Hey class, what we got here is just a quick little video that kind of goes over how to understand centripetal acceleration and how we calculate it from the change in velocity. Alright, let's see if we can go through a quick explanation of how we calculate acceleration. So, let's imagine we have some velocity vectors. Let's just do linear first. So, we're going to start with a velocity vector. That's our initial velocity. And we're going to speed up. So that's going to be my final velocity, right? Now, how do we figure this out? Well, let's take a look at it from this point here. I'm just going to make a little red dot here. We're going to assume that that is our starting point for reference. Now, we're going to have our initial velocity, and then we're going to speed up, and now we're traveling faster. There's our final velocity. So how do we calculate acceleration? Well, acceleration is Vf minus Vi divided by t. So it depends on how long it takes to make that transition. So if we look at Vf and then we subtract Vi, we can see that we have a certain distance that represents our change in velocity, which is what we have down here. Our Vf minus Vi is our change in velocity. So simply have a change in velocity, and so obviously that is a change in velocity forward or to the right divided by a certain amount of time. Now, how does this look in circular motion? Alright, so we can imagine something driving in a circular path. We're going to examine 2 points. Now, what would happen if we had some velocities at those 2 points? We're going to call this Vi, and we're going to call that Vf, right? So it's moving in this direction. The velocity is going to be tangent to the curve. What that means is, if we were to draw a line, we would adjust it so that it is touching the curve at one point. That's tangent to the line, or tangent to the curve. That represents the direction of the velocity at that particular point in time. So that would mean if we put our velocity vectors on there, we would have an initial velocity, and we would have a final velocity. Now, if something was traveling in a constant speed, right? So basically the magnitude would be the same. So if it was 100 kilometers per hour going through the curve, it's still 100 kilometers per hour at the Vi and the Vf point. However, the direction has changed. So the velocity vector has changed, even though the speed hasn't. Now we can calculate the acceleration as well here. We would just simply take Vf, which in this particular case, there's my final velocity, and we would subtract from it our initial velocity. So all we would need is just to flip that around and keeping it tangent. Now it's really important that I make sure that even though I got a negative Vi shown now, that we keep the direction the same, because the direction is critical. So now if I take my Vf and I subtract my Vi, you can see we can now measure the change in velocity. The change in velocity would be in that direction. So much like our first example, acceleration is equal to Vf minus Vi divided by t. So there's obviously a change in velocity, because if we obviously look at the diagram, we can see from where we started, there's a change in velocity. And of course that would occur over a certain amount of time. The key thing here is to notice that the direction of the acceleration is not along the perimeter or the circumference of that circle. The direction of the acceleration is inwards. And in fact, my curve isn't perfect here, but it's directed inwards towards the center, wherever that would be, somewhere in here based on that curve. So that's how we visually represent centripetal acceleration in a diagram, showing how if we simply measure the final and initial velocities, we can calculate the acceleration and the direction. So hopefully that helps with your understanding of centripetal acceleration. And if this little video doesn't help, feel free to go through the notes and see if you can get some more information out of that. Maybe that's more helpful to you. Good luck, and we'll see you next class.